In day 4 of chapter 12, we're going to begin with a review of the things we've covered so far in this chapter. So the first thing that we did talk about in this chapter was the length of an arc. And the length of an arc is usually denoted with a capital L. And first we need the fraction of the circle. So the fraction of the circle is the number of degrees. Here's the degrees. Divided by 360, because 360 is a full circle. And then times 2 times pi times the radius. And they gave us the radius on this one, 5 inches. Now in this particular problem, it tells us to round our answer to the nearest hundredth. So we'll be putting all of this into our calculator, including the pi, and then rounding to 2 decimal places, and we get 13.70 inches. And that was an arc length problem. Now, we also had some problems in that first section on arc length where we had to find the circumference of a circle, and they gave us some information about the arc length. This is one of those such problems. In this problem, we actually are given information about a part of the circle. We're given the number of degrees in the part, and we're given the arc length of the part, and then they ask us for something about the whole circle, in this case the circumference. And this is where we use a proportion. And we compare the part to the whole circle. And let me just review that with you. So the part was 18 degrees, and the full circle is 360 degrees. The arc length on the part was 9 centimeters, and we're looking for the circumference of the whole circle. Now, once you have it set up, we always solve proportions in the same manner. We always cross multiply. So 18 times c would give me 18c. And then 360 times 9 would give me 3,240. We would finish this one by dividing, and we come up with the circumference is 180 centimeters. Now, in that first geometry section of chapter 12, we also talked about area, specifically area of a sector. Here's one of those such problems. When we're finding the area of a sector, we again first needed the fraction of the circle. So they gave us the degrees, and then they gave us also the radius. To get the fraction of the circle, we would put 42 degrees divided by a full circle, which is 360 degrees, times pi, and then times the radius squared. This one also asked us to round to the nearest hundredth, so we're going to put all of that into our calculator, including the pi symbol, and the area of the sector here, if we round to 2 decimal places, comes out to be 71.84 inches squared. Now, like happened with arc length, sometimes they'll give us information about the part of the circle, and they'll ask us for the area of the whole circle. Here's one of those such questions. So in this one, they ask us to find the area of the whole circle. And they give us the number of degrees in the part, and they give us the area of the part. So as we saw in problem 2 today, we're going to use a proportion. And in our proportion, we're going to compare the part of the circle to the whole circle. So for example, the degrees in the part, 72 degrees. The degrees in the whole circle, of course, 360 degrees. The area of the part, 24 square centimeters. And we're looking for the area of the whole circle. And as we saw on problem 2 today, we will cross multiply, as we always do in proportions. 72a equals 360 times 24 gives me 8,640. Dividing by 72 to finish, I get the area of this circle is 120 centimeters squared. After we had finished talking about arc length and area, we began talking about segments in circles, and that was the section right before this. Let's review those that we've talked about. In this particular problem, we have what are called secant segments. Secants intersected the circle at 2 points. Secant segments are a part of those secants. And for secant segments, the pattern we tried to remember was outside times whole length has to equal outside times whole length. And I encouraged you to label the outside, or the whole length on each of the segments. So for example, on this top one, which I've highlighted in blue, the whole length there would be if we add those two together, x plus 5. On the bottom one, which I'm highlighting in green here, the whole length would be 9 plus 3, which is 12. So if we do the blue one first, on the blue one then, we'll have to take the outside, which is x, times the whole length, x plus 5. Then on the bottom one, which is the green one, we'll take the outside, which is 3, times the whole length, which is 12. The rest of this problem is algebra. We have to distribute x squared plus 5x equals 36. As we saw in an earlier section, this is one where it's going to be solving a quadratic equation. We have to move the 36 over. We accomplish that by subtracting. X squared plus 5x minus 36 equals 0. This time we'll be able to solve by factoring. And to solve by factoring, we have to, of course, first factor. This is a general trinomial. To get that x squared in the front, we need x and x. And to multiply to get 36 and subtract to get 5, we'll have to use 9 and 4. And to get a positive 5, we'll need a positive with the 9 and a negative with the 4. We set each of those equal to 0. Subtracting 9 on the first one, I get negative 9. Adding 4 on the second one, I get 4. And this will be our only answer. And again, you must box your answers. If you don't box your answers, it's wrong. The negative 9 doesn't work in this problem. There will be some in this chapter where the negatives will work perfectly fine. This is just not one of them. Let's try another one of these with secant segments. Now, this one has a secant segment, but the other segment is called a tangent segment. As we just reviewed, for the secant segments, you take outside times the whole length. But for a tangent segment, you only have an outside. So you actually take outside times outside. Now the secant segment is the one that I've highlighted here in blue. And we'll want the whole length on that one. The whole length on that happens to be 10. The tangent segment is the one I've highlighted here in green. So for the secant segment, we'll take outside, which is 4, times the whole length, which is 10. And then for the tangent segment, outside times outside. 4 times 10 is 40, and x times x is x squared. This one we can solve by using square roots. And that was a technique that we reviewed back in the first week of this chapter. We've isolated the squared one already, so we'll take the square root of both sides. There are 2 answers algebraically. One of them would be x equals the square root of 40. The other one will be x equals negative square root of 40. Now, the negative one won't work here. But the positive one does, and it didn't tell us to round. So we'll have to break this down. We'll break it down into 4 times 10. 4 will break down into 2 times 2, 10 into 2 times 5. Because we have two 2's, we can take a 2 out, and inside there we'll still have a 10. So this would be our answer, since they didn't ask us to round. One more review problem before we move on to something new. Now, in number 7, these were called chord segments. And the pattern we remembered for chord segments was first part times second part equals first part times second part on the other chord segment. Let's take them one at a time. Let's take this blue one. On the blue one part is an x and the other part is x plus 8. So I have x times x plus 8. On the yellow one here, one part is 4 and the other part is 5. And the rest is algebra. X times x is x squared. X times 8 is 8x. 4 times 5 is 20. This once again is a quadratic equation, so once again we have to move the 20 over. X squared plus 8x minus 20 is equal to 0. This one once again will use factoring, and it is a general trinomial. So x and x to get x squared, multiply to give us 20, subtract to give us 8. I'm going to have to use 10 and 2. To get a positive 8, I need a positive on the 10 and a negative on the 2. Setting each of those equal to 0 to finish solving. I get x equals negative 10, which doesn't work in this problem, and I get x equals 2. So 2 would be my answer. Okay, enough with the review. Let's move on to some new things. So here's a new concept. And this concept says if we have two tangents to the same circle, they have to be congruent. So if two tangents are congruent, that means they are equal. These would be congruent. Two tangents from the same point to the same circle have to be congruent. But that really means tangent equals tangent. So for this one, we would just set the blue one, 2x plus 4, equal to the yellow one, which is 24. And then we just solve it. So now it's algebra. We'll subtract 4. We'll divide by 2. So two tangents to the same circle from the same point are congruent or equal. Here we have another of that same thing. Two tangents to the same circle from the same point will be congruent. So these two are congruent. That means the blue one right here, x squared plus 3, will equal the yellow one, 19. Now this one's a quadratic, so we're going to solve it using square roots. We'll subtract the 3, x squared equals 16, and then we'll take the square root of both sides. And when we take the square root of both sides, we have two algebraic answers. One of them is x equals 4. The other is x equals negative 4. This time, both will work. Both work this time because when we check, negative 4 squared plus 3 would be 16 plus 3, which is 19. And of course, the positive one will definitely check as well. 4 squared plus 3, 16 plus 3 is also 19. So they both check. And once again, you must box your answers. If you don't, it is wrong. So as you can see, sometimes the negatives will work. Let's try another problem. This is another one where we have two tangents. So they will be congruent or equal. The blue one, this top one, x squared minus 6x plus 5 will equal the bottom one, the yellow one, x plus 23. And now comes the algebra. In our algebra process, we'll have to move the x over, we'll have to move the 23 over. That will give me x squared minus 7x, and then negative 18. Now, this one, I think we can factor. So we'll make two sets of parentheses because it's a general trinomial. X and x will give me x squared. Multiplying to give me 18 and subtracting to give me 7. 9 and 2. To get negative 7, I need a negative on the 9 and a positive on the 2. Setting each of those equal to 0, I end up with x equals 9 and x equals negative 2. When we substitute these back in, once again, they both work. When we check. And you must box your answers, or it is wrong. Okay, let's try yet another one. And this one's a new one. So this is a new concept. And in this concept, it says, if you have congruent chords in the same circle, then you have congruent arcs. So congruent chords have congruent arcs. Congruent chords have congruent arcs. When we look at this problem, they didn't tell us what this arc was out here. That isn't labeled. So we're going to find this first. Find this arc first. And to find it, we'll take the full circle, which is 360. We'll subtract the 91, and we'll subtract the 178. And what do you know? That particular arc comes out to be 91 degrees. So we have congruent arcs. So that means we have congruent chords. So this chord, the 2x plus 3, will equal this chord, the 21. 2x plus 3 is equal to 21. We subtract the 3, and we divide by 2. Let's try another one. This is another new concept. In this particular concept, we have a diameter that is perpendicular to a chord. Now, a diameter perpendicular to a chord bisects the chord and its arc. Let me write that down for you. A diameter that is perpendicular to a chord bisects the chord and bisects its arc. So what we look for is, first of all, a box to show that it's perpendicular. If it's perpendicular, we would know that the chord is cut into two equal parts. Those are congruent. And the arc is cut into two equal parts. So those two arcs are congruent. Of course, in this one, we're only interested in the chord. So we would know the 3x would be equal to the 12. so x would be equal to 4. So a diameter perpendicular to a chord bisects the chord and bisects the arc. Here we have another of those type of problems. We have a diameter, that would be the PQ, and it is bisecting, it is perpendicular to a chord. And that's what this little box is telling us. So we know it will bisect the chord and bisect the arc. That means that these two chord pieces are congruent and these two arcs are congruent. Once again, we're only interested in the chord being bisected, so the 2x plus 3 will equal 15. Subtract the 3, so x would be 6. Okay, let's check out another one of these. So as you can plainly see, once again, we have a diameter perpendicular to a chord. So we know it's going to bisect the chord and bisect the arcs. So that means I know this piece is equal to this piece, and I know these two arcs are also congruent. Well, they actually gave me D to E. D to E is the whole thing. D to E, that whole thing, that's 20. And then they gave me information about F to E, this piece right here. That F to E is 3x plus 2. Well, if it's bisected, the D to E, then that F to E is only going to be half of it. So if I take 20 and divide it by 2, I find out that the 3x plus 2 has to be equal to 10. I'll subtract 2 and divide by 3. Since it doesn't tell us to round, I'll have to leave this as a fraction. Let's try another problem where we have one of these diameters perpendicular to a chord, but they ask us for something a little different. So in this particular problem, we do have a diameter perpendicular to a chord, so there's perpendicular. So when we have this diameter perpendicular to chord, we know we bisect the chord and the arc. So that means that I know this piece is equal to this piece, and this arc is equal to that arc. But let's see what they've given us. So they gave us A to D. They gave us the whole length, A to D. This whole thing was 34. That's the diameter. And then they gave us that C to D was X right here. Whoops, sorry about that. Let's find the radius first. So as our first step, I suggest we find the radius first. The radius is just going to be 34 divided by 2. It's half of the diameter. And the reason I think that's going to be so helpful is I can draw in a radius that goes from B to E. So that's my radius right there. That's 17. And then because they gave me the length from E to F was 20, so E to F is 20, I think I know this piece right here. From E to C. And all of that will allow me to find B to C. So our plan is to find B to C using the Pythagorean theorem. I have 17 squared equals, I'm going to call that y for the time being. So y squared plus 10 squared. And 17 squared works out to be, let's check that out, 289 equals y squared plus 100. Subtract 100. Oh, I'm sorry. C to E actually is 10. Is not 10, rather. C to E is going to have to be 15 because the whole length there was actually 30. I apologize for that. So that's going to change this to a 15. So this was 15 squared. So that's 225. Subtracting, we get a much nicer number. We get 64. When we take the square root, we get y equals 8. Y equals negative 8. Now this one doesn't work in this problem. But now I know that b to c equals 8. And I know to b to d is equal to 17. So to find my x will equal 17 minus 8. So x will equal to 9. Now that was a pretty involved problem. Let's do one last problem and then we'll be done for today. In this particular problem, we have a secant segment and a tangent segment. For our secant segment, we remember we take outside times whole length. And for our tangent segment, we take outside times outside. So let's talk about the secant segment. The secant segment is this highlighted blue one. We're, of course, going to want this whole length right here. That whole length will be x plus 2,000. Big numbers, but we get to use a calculator. So for the secant segment, the outside being x and the whole length being x plus 2,000, that would be our left side. For the tangent segment, the one that's highlighted in yellow here, we have 2,400 times 2,400. And now it's algebra. We'll have to distribute x squared plus 2,000x equals 2,400 times 2,400, 576, 0, 0, 0, 0. Moving everything to one side, so we have 0 on one side. Now, I'm pretty sure this one doesn't factor, and in any case, those numbers are huge, so we're going to use that quadratic formula. The a in this problem is 1, the b is 2,000, and the c is negative 576 and 4 zeros. When I put the numbers into the quadratic formula, I will have x equals negative 2,000 plus or minus the square root, and then I have 2,000 squared minus 4 times 1 times negative 576 with 4 zeros. All of that divided by 2 times the a. Working out what's beneath that square root sign, I'll have negative 2,000 plus or minus the square root, and then underneath that square root sign, I have 2704, and then 4 zeros. And all of that's divided by 2. We know from our experience that this splits into two possibilities. One is when we use the minus, negative 2,000 minus the square root of 2704, 1, 2, 3, 4 zeros divided by 2. The other one we use the addition sign, x equals negative 2,000 plus the square root, and then 2704 and 4 zeros, all divided by 2. Now on that top one, when we round it, and it asks us to round this time to the nearest foot, So we're going to the nearest whole number. On the top one, we get x equals negative 3,600. Yeah, that's not possible. We can't use that as a distance in this problem. On the bottom one, we end up with 1,600. So you have to travel 1,600 feet along that trail to get your cell reception. The last one, again, was pretty involved. You will see problems like that on your test and on quizzes. So good luck on it. If you